Hey guys, welcome back. We are going to continue with surface area today. The last notes that we took, we did surface area of prisms and cylinders. And so today we're going to look at pyramids and cones. So we'll kind of follow that pattern. We're looking at surface area of those four things. So pyramids and cones today, and then cylinders and prisms the other day. And then we'll jump in the next week or so, next lessons to volume of those four shapes. So that's kind of where we're headed, but we're going to look at the surface area of pyramids and cones today. So just kind of a reminder that a pyramid is polyhedron. It has one base, and then all of the lateral faces, they come to a point, which is called the vertex. You name it by the shape of its base. And then the altitude is basically the height of the pyramid. That would be this right here. But then we're also going to have, or like this in this case, we're going to have the height of the sides of the pyramids or cones. So they call that slant height because it's basically a slanted height. So that is, do that in red, that is this right here. So it is like the height of the side of the pyramid when it's slanted. So like there's a triangle on the side of the pyramid, and it's the height of that triangle. So let's start with a pyramid. They said the lateral area is 1/2 times the perimeter times the slanted height. I like to stick with you can memorize that shortcut if you want. I still go with lateral area is the area of all the lateral sides. So I would just take each of these triangles and add those areas up. So 1/2 times base times height, and the height is the lateral height in this case. So 1/2 times the base times the height, and then however many of them there are. So in this case, it looks like there's 4. Or you can use their shortcut. Surface area is still the lateral area plus the area of the base. So there's only one base in this case instead of 2 like before, just the bottom of the pyramid. So let's do a couple of these. We'll start with a basic one. This is called a square pyramid. So if I want to find the lateral area, I'm going to find all of these triangles and add them all up. Since it's a square, they're all the same. So I'm just going to take one of them and multiply by 4. But I would have 1/2 times base times height. That height is the slanted height in this case. So the base would be 6. And the height would be that, they call it like a curvy L, slanted height, the L in slanted, times 10. And that would give me 30. So the lateral area, which is again all the lateral sides, the area of those, that would be 30 plus 30 plus 30 plus 30, which is equal to 120 meters squared. So that's the lateral area, and I'll shade it would be this triangle and this triangle. They're all the same. This one. And of course the one in front. It's kind of hard to draw, but all of the sides of that pyramid, the lateral sides, 120. Then if I wanted the surface area, I would just take that lateral area and add the area of the base. Since this is a square, it's a nice and easy one. 6 times 6, that base is 36. So I would say that would equal 120 plus 36, or 156 meters squared. So that's kind of the basics of it. I picked some fairly easy shapes there. I'm going to add a little bit harder shapes so that you can see how to do those. So This one, number 2, is a hexagonal pyramid. It's a hexagon. It has 6 sides. They're all 5 meters each. It shows us the slanted height of 6.9 meters. So finding the area of that base is going to be a little bit harder than a square. We'll have to remember some things from last chapter. But let's start with the lateral area, which is the area of all the lateral sides or faces, whatever you want to call them. Since they're all triangles, and I'm not going to shade every single one of them in, but they are going to all be the same. This is a regular hexagon. So that would be 1/2 times base times height for those sides of the pyramid, the triangle. The height, again, is our slanted height. So 1/2 times 5 times 6.9. I'll do that one in my calculator. And I got 17.25. So to add them all up, I'm going to add them up 6 times, or because I don't feel like writing it 6 times, I'm just going to multiply by 6. And I got 103.5 meters squared for the lateral area. So that is all 6 of those triangles on the side. I do need to add in the area of the base if I want to find the surface area. So that's the lateral area plus the area of the base. And that is a hexagon. So we're going to have to go back. This is 103.5. We're going to go back to what we remember for finding the area of a hexagon. So I'm going to kind of draw that out. It's been a while since we've done that. If I have a hexagon, see if it'll, oh, nice. So I have a hexagon here, and we're going to have to find the area of it. So back to what we did in chapter 9. Break it into 6 pieces. The only thing I know is that this is 5 meters. So go back to all those steps I saw you guys recently do on your test. Good job with that. They are 60 degrees each, which means that's 30, 90, 180 minus 90 minus 30 gives me 60 right here. And this would be 2.5 and 2.5, that 5 cut in half. So this is what I'm going to try to find so I can do the area of that base. Hopefully this is familiar. Let's go with, I'll look at the 60 degrees. So tangent of 60 is opposite, which was x, over adjacent, which is 2.5. Multiply both sides by 2.5, and I'm going to get 4.33 equals x. So that is the height, or our apothem, of the hexagon. So the area of one of those triangles would be 1/2 times the base, which is 5, times the height, which is 4.33, which gives me 10.825. And the area of the hexagon would be that times 6, which gives me 64.952 meters squared. So we got to go back up here. And the surface area is 103.5 plus the area of the base, which was a lot of work, a lot more difficult than the square, but that was 64.952. If I get this out of the way and add those together, I will get, type it in my calculator, 168.45 meters squared. So sometimes the area of the base is easier to find, like the square. We just did 6 times 6, and sometimes we have to do all of this to remember hexagons and pentagons and those sort of things. But the formula is still the same. Lateral area is just all of the areas of the lateral sides added up. And then surface area is just the lateral area plus the area of the base. So the last time we learned it was both bases because cylinders and prisms have a top and a bottom, but pyramids and cones just have a bottom. So only one base. So let's move on to cones. Same exact thing. The lateral area is the area of all the lateral sides. And the surface area is the lateral area plus the area of the base. The hard thing with a cone is it's really just kind of one lateral side that's curved. So a couple things. Again, the altitude, this is the height of the triangle. And just like before that slant on the pyramid, this is called the slant height. It is what you would do if you kind of were thinking about the pyramids. It's like the slanted height of the pyramid. So that is the height on the slant. So the regular height I have in red, and then the slanted height I have in green. Side note, if you see any of these problems, sometimes you have to do Pythagorean theorem to find one of them. If you have the radius of the circle, you might have the slanted height and you need the altitude, or you might have the altitude and you need the slanted height, and you're going to have to do a squared plus b squared equals c squared to figure out your missing piece. So that could be coming. So what we're going to do is the lateral side, this is their formula kind of boiled down. I think of it, this area of the lateral side, it's kind of triangular. That's where the 1/2 comes from. And it is the circumference times the slanted height. I'll write that out. It's just like the pyramids on the side. They had triangles on the side, 1/2 times base times height. It's just the circumference is the whole base, and the slanted height is our height, just like before. So 1/2 times circumference times slanted height. If you want to see how they got this really quick shortcut, what they did there was circumference is 2 pi r times slanted height, and then they canceled these, and they got pi r L for just a shortcut for the lateral area. So if you want that shortcut, you can use it. Then surface area, again, is still just the lateral area plus the area of the base, and there's only one of them. So let's go ahead and practice these together. We'll start with one where they give us the slanted height. That's nice and easy. They did throw us for a little bit here. They gave us the diameter, which is 4. Diameter equals 2 times radius. So 4 equals 2r. Divide both sides by 2. And the radius is 2 centimeters. So they did give us the slanted height. So if I want to find the lateral area, again, this would be, if you think of a birthday hat or a waffle cone, it would be the amount of material that you're using. So that's kind of the application. So this lateral area would be that 1/2 times circumference times slanted height. The slanted height is 6 in this case. The circumference is 2 times pi times radius, which is 2. And then we'll get the lateral area to be 12 pi. If you would like a decimal, that is 37.699. The unit would be centimeters squared. So that's not too bad for the lateral area. Let's go ahead and add the base to it. So surface area is lateral area plus the area of the base. The area of the base would just be the area of a circle in this case, so that would be pi r squared. Lateral area was that 12 pi, and our radius was 2, so pi 2 squared, and our surface area is 12 pi plus 4 pi, or 16 pi centimeters squared. Or again, if you would rather that in decimal form, it is 50.265. So there's kind of your surface area, and this is your lateral area. That was not too bad. They gave us the slanted height, but sometimes they do not give us the slanted height, and they make us solve for it. So we'll do this next one together where they make us solve for it. So they gave us this time the altitude, and they gave us the diameter and the radius. Well, they didn't give us the radius, but we can solve for that. Diameter equals 2r, so 13 equals 2r. And that would either be 7.5, 7.5, or you can just leave it as a fraction form. I'm sorry, not 7.5, 6.5. So if you would like to do it in decimal or a fraction. So we're going to have to do a little bit of Pythagorean theorem here to figure out what this slanted height is. I don't know if you see, I'll draw it in purple. We've got a right triangle right here. And I know that 13 over 2 is my a, so a squared plus b squared, which is our 10. And that will give us our slant, or our slanted height, our c squared. So that's 169 over 4. Again, you can do this in decimals. I'm just going to stay in fractions as long as I can for the ACT. Then that is the same as 400 over 4. 100 is just 400 over 4. So I have 569 over 4 equals c squared. The square root of 569 is a decimal. So I'm going to have to break it down like this. I'm trying to think of what goes into 569. Okay, 569 is actually a prime number, so that is why I couldn't figure anything out to divide it. So we're going to have the square root of 569 over 2, that was the square root of 4, equals our slanted height. So if you would rather do that as a decimal, that is 11.927. So then we can follow our formula. Put this off to the side. And our formula for lateral area is 1/2 times circumference, which is 2 pi r, times the slanted height. So that would be, those would cancel, pi rl. So pi times the radius times the slanted height. Again, you can use decimals. I'm just trying to show this for the ACT. The lateral area is 13,569 under the square root over 4 pi centimeters squared. That looks a little crazy, so I'm going to go ahead and type it into my calculator. You should get 243.55 centimeters squared. So that is your lateral area. If you want the surface area, all you got to do is add on the area of the base. We'll stick with decimals for this one. 243.55 plus the area of the base is pi r squared, or pi times 6.5 squared. 6.5 squared is 42.25 times pi gives me 132.73. If I add that together, I will get 376.28. So if you're wanting to find how much material you would need to cover this, that would be the amount. So that's what this is kind of useful for. Since we only have notes today, I'm going to throw on, this one will be a little bit longer. I think we're around 20 minutes or so, but I do want to throw some challenge problems on there. Since we don't have any extra homework today, we're going to do that next week. So what happens if you do something like this? It looks a little bit different. Let's jump in. We'll pick one of these. How about, let's go with the cylinder. This looks interesting. So we've got a cylinder with a cone on top. So we're going to have to do a couple different things. They want the surface area, and we're going to need to do the lateral area to be able to find that. So let's just start with the cylinder only. So I'll highlight the cylinder. So we are just finding the cylinder. Normally, I would do the top and the bottom of the cylinder, but the top of the cylinder isn't gonna need covering because the cone already covers it. So that's what makes this a little bit different. So if you were doing your lateral area, you would take going back to cylinders, the circumference times the height was one of our formulas for lateral area of a cylinder. My circumference is 2 pi r, and then times my height. So 2 times pi times 10, and then that height is 40. So it looks like I've got 800 pi. Let me double check that. 800 pi. And then you could turn that into a decimal if you'd like. That's the lateral area. Now for the surface area of that purple cylinder, normally plus area of the bases. Usually I would add both bases, this one down here and this one up here. But this one I'm not going to add because the cone is covering it. It is sitting on top of it, so that it will not actually need to be painted or covered with wrapping paper or covered with material. So it's really going to only be one in this case, which throws it off a little bit from what you would think. So 800 pi, and then the area of just the one base, we're only using the bottom this time because the top is covered by the cone, would be pi r squared. That radius is 10, so it would be 800 pi plus pi 10 squared. That would be 100 pi plus the 800 pi gives me a surface area of 900 pi. We could turn that to a decimal if we'd like. Now again, that is just the purple shape. We did not do the top of the purple cylinder because it's covered up by the cone. So let's look now. We'll do an orange, this cone. So normally when finding the surface area of a cone, I would find the surface area of that bottom of that cone. But again, it is being covered by the cylinder. So we don't need to actually find the base of that because it's being covered up. It doesn't actually need to be painted. So when we're doing this, we really only need the lateral area. So lateral area for a cone is 1/2 times circumference times height. And the height in this case is the slanted height. They gave that to us already, which was nice. So 1/2, the circumference would be 2 pi r. The slanted height, I'll use a little L to show. So the lateral area is 1/2 times 2 pi times 10 is the radius. And then that slanted height is 26. These will cancel out, and the lateral area is 260 pi. Again, normally when finding the surface area, I would do the lateral area plus the area of the base. But I don't actually need to add the area of the base in this case because it's right here and it's being covered up by the cylinder. So my surface area is just the lateral area, 260 pi. So if I add that orange shape and that purple shape together, I'll have 900 pi plus 260 pi, and that will give me, I believe, 1160 pi. Let me double check that. Yep, 1160 pi, and then if you want that as a decimal, that is 3644.247. So 3644.247, and my unit would be inches squared. So again, if you're trying to find out the material to cover this shape, that's how much you would need. You don't want to buy or pay for or waste your time with this because it is covered. So that circle is covered with covered by the cone and covered by the cylinder. So you're not actually going to need to paint that. So that is why we left it out. So those are kind of the tricky ones. If you want to do one like this on your own, feel free to. You have some triangular shapes in there, but for the sake of time, I just thought I'd try one of those tricky ones. That's all for today. Make sure to submit your notes and have a great day.